All right, so if we know that isotopes are a mixture of elements with different masses, same element, different masses, most elements occur as a mixture of these isotopes. And so we can tell, based on looking at the periodic table, what the most abundant isotope is for most atoms, right? We had a question like this on the test. Which isotope is more abundant for magnesium, 24 or 25? So how would we know that? How do we know which isotope is more abundant for magnesium? Yeah, we look at the periodic table. If this mass that's given, 24.3, if this mass is 24.3 and this is a weighted average, that means that 24 isotope must be more abundant than the magnesium 25 isotope, right? That's how we looked at that. If you look, let's say, at oxygen, what do you think oxygen's most abundant isotope is? 16. Is its second most abundant isotope weigh more than 16 or less than 16? Less, right? Because the weighted average is pulled down slightly to be 15.999. Right? So the closer it is to a whole number, that means that element has a really, really dominant isotope. Okay? And it has a few others, but they're not as prevalent. So that means it's got a really dominant isotope. So the average atomic mass is what goes on the periodic table, and it takes into account how much of each isotope is present and what that isotope weighs. Okay, so it's essentially a weighted average of all of the naturally occurring isotopes, and it's used with this formula. You've seen this one before. We use this in Chem 1 just a little bit, really only with this chapter. We take the percentage of abundance of isotope A times its mass plus the percentage of abundance of isotope B times its mass. You do it with as many different isotopes as you get, right? If an element has 6 stable isotopes, you'd have 6 different things you're adding up, okay? And it will give you a weighted average. So in this example here, I think I gave you copper. It's 69.17% abundance of an isotope that weighs 63, and then 30.83% abundance of an isotope that weighs 65. So if I was going to calculate the average atomic mass, can I leave that as a percentage, or do I need to put it into a decimal? I need to put it into a decimal. So I'm going to go 0.6917 times 63 plus 0.3083 times 65. So go ahead and run the math on that and see, should our weighted average come out closer to 63 or closer to 65? Should our average atomic mass come out closer to 63 or closer to 65? I think it should come out closer to 63, right? Because that's the more abundant isotope. 69% of atoms that are pulled out of samples of copper have a mass of 63. So it makes it the most abundant. Tell me, what did we get? Like 63.5 or something? 63.6166. Okay. So we would call that our average atomic mass 63.62 if you wanted to. Okay, and units would be AMU. Okay, does that make sense how average atomic mass is calculated? Yeah, Faith. Try this one on your own. It's important here to make sure that we do convert those percentages into decimal places. So you need to move it 2, right? Good. All right, what did we get as our weighted average here? 33.25?
044. I just read it.
Okay, that's fine. Oh, I wrote only 3. 33.2. Okay. All right, so we need to start thinking now about the difference between atomic mass and molar mass. What do we know the difference between those are?
Molar mass is...
No, Lauren? Yeah, answer it all for us.
What's the difference between atomic mass and molar mass? Yeah.
Atomic mass is for one of the element, molar however many moles of an element.
Yeah, very good. Atomic mass is how much one single atom weighs. Molar mass is how much the mole of that substance weighs in grams. And so atomic mass is measured in AMU, and molar mass is measured in grams per mole. Okay? Numerically, they're the same value, but they represent very different quantities based on the units themselves. Okay? So the ratio and that number in terms of its mass are the same, but the units mean something very different. So we can calculate molar mass and atomic mass of both elements and compound. Molar mass is given on the periodic table just like atomic mass is, but atomic mass is measured in AMU, just stands for atomic mass unit. Okay, and it's singular molecules. So AMU is talking about this many protons plus this many neutrons weighs this little tiny amount of AMU. But molar mass is measured in grams per mole. So it says if we put 1 mole, 6.022 times 10 to the 23rd, we put that many molecules on the scale, it would weigh that many grams. So the number it represents is the same, right? For carbon, its molar mass and its atomic mass is 12, right? But the units mean different. Which one do we use more often? Molar mass, for sure. Molar mass, for sure. Okay. If we want to find molar mass, we got to take into account the molar mass of all the individual atoms in the compound. Okay, I think molar mass should be an easy review calculation here for us. Would we agree with that?
Yes.
Okay, molar mass should be easy. So if I'm going to find the molar mass of H2SO4, let's go ahead and do that. How many hydrogen atoms do I have? 2 hydrogen atoms, and they each weigh 1. Plus, how many sulfur atoms? And it weighs how much?
32.
It weighs 32. And then how many oxygen atoms do I have?
4.
And how much do they weigh?
16.
Right. Okay, so you can write it out as much as you need, but we need to go ahead and calculate molar mass. I think it'll be something that you can just do in your calculator. You don't have to write out every time. 2 plus 32 plus 64 gives me a molar mass 98 grams per mole. Okay. That should be something we feel pretty comfortable with from Chem 1 is calculating molar mass of compounds. What do we do if it has parentheses in it? We distribute that parentheses. So how many nitrogen atoms do we have?
3.
Okay. And they weigh 14. How many hydrogen atoms do we have?
12.
Good, 12, not 7. Okay, a lot of people want to add those two. We don't do that. We have 4 hydrogens per ammonium atom or per ammonium molecule. I'm sorry, I misspoke. And we have 3 of those ammonium molecules. So 4 times 3 is 12. And then how many phosphorus do we have? Just 1. And then oxygens, again, we have 4 that each weigh 16. So 14 times 3 is plus 12 plus 31 plus 64. 149
Yes.
grams per mole. Okay, we feel good with the parentheses part of it? We're just distributing that through. Very good. All right, now if we start to talk about something called percent composition, what does that mean?
How much of each element?
There we go. We're finding the percent of each element within a compound. So after we find the molar mass of a compound, we can break down that molecule into its percent composition. What is it composed of? Okay, all we do is we're comparing the mass of the element within the compound to the mass of the whole thing. So you're taking the part over the whole. Okay, so if I wanted to find the percent composition of CH5OH, first thing I have to do is find the molar mass. Okay, that's the very first thing I need to do is find the molar mass of that molecule. So C2H5OH has 2 carbons that each weigh 12. How many hydrogens does it have in total?
6 plus 14.
It's got 6. And what's the molar mass of oxygen? 16. Okay, so 24 plus 6 plus 16 gives us a molar mass of 46. Okay, And so when it asks for percent composition, that means we want the breakdown of every element that's in that. It's not just, we could say, what's the percent of carbon in this? And we would just have to do carbon. But when it asks for percent composition, we want each element. So let's do carbon first. Within this molecule, how much does carbon weigh?
24.
Yeah, it doesn't just weigh 12 because there's 2 of them. So we'll take 24 divided by the total, which is 46. 24 divided by 46 gives me 52.2%. Okay, hydrogen is our next element. How many hydrogens are in this molecule in total? Right, so I'll take the part divided by the whole. And I get 13%. And then my last element is oxygen. That part is just 16 out of 46. And I get 34.8%. And so how do I check my work here with percent composition?
Add them all together, see if it makes 100.
Very good. My percentages should all add up to 100 or very, very close to it. Okay, so you don't have to add that up, but just looking at it here, we should be right at 100, right? And usually we're going to try to pull these to the 10th place if we need to. That'll help us be a little bit more exact. But that's what we're looking for, percent composition. If it would just ask what's the percentage of carbon, I would have only had to do this portion of my problem. But if it asks for percent composition, that one means I want to know the composition of the whole thing. Okay? All right. Oops. Sorry. Okay. All right. Moving into... Actually, I want to go ahead and stop. I don't want to do empirical formulas, so... All right, we're going to use... what's the conversion factor we use to go between grams and moles?
6.022.
Nope.
Nope, that's for molecules and moles. What do I use if I want to go between grams and moles?
Molar mass?
Molar mass, right? Anytime we see the word grams, we got to be thinking molar mass. Grams is molar mass because molar mass is measured in grams per mole, right? So if we're talking about gram and mole conversions, we use the molar mass to help us convert. So let's start here with just some problems. Oops, I went too many. All right, how many moles are in 74.2 grams of magnesium chloride? Right, these are T-chart conversions, and we always start with what?
What we know.
What we know. 72 grams of MgCl2. Okay, yeah, I might have said it backwards. 74.2 grams of MgCl2. I need to get rid of grams, so where does it go?
Bottom.
Good, MgCl2. And I want to go to moles, so it goes on the top.
So what? Something plus 70.
Okay, and then what do we always know about moles? What does it always get?
1.
The 1 for now, right? Until we get into mole ratio stuff. But for right now, it gets the 1. And then what number always goes with grams?
Molar mass.
The molar mass. Good. So you need to calculate molar mass of MgCl2. I had that molar mass come out at about 95.3, if that's what you guys had as well. Okay, I keep chlorine at 35.5, so times 2 is 71 plus 24.3. Magnesium, I don't round. I don't think that's close enough. So now I'll look at my units here and say, okay, I canceled grams. I'm left in moles, which is what I want. And then I just do the math. So I multiply across the whole top, divide by the whole bottom. Is that coming back to you? Does that phrase like haunt your dreams?
Oh, yeah.
0.779 moles. I'm kind of just choosing 3 sig figs there to finish that problem because I started with 3 sig figs. So that's kind of where I'm choosing to round that at. That's going to kind of be our rule of thumb here for these problems is we're going to put ours into the same number that we started with because these numbers, molar mass here, are considered exact. So we don't take them into account for our significant figures calculations. You'll kind of go based on what your measurement started with. Okay, so I got 0.779 moles of MgCl2. Why don't you do the second one on your own? 195.76 grams. So what did we say about our significant figures?
Add them up. Round them up.
Okay, so we should have probably rounded to what?
196.
196 grams probably. Right? 3 sig figs probably needs to mean that we round up. Again, not something I'm going to be hugely concerned with, but something I'm going to try to bring up more often because it's just a little bit more important as you get close to those like college chem classes. So, of calcium nitrate. Yeah, first you got to build the compound. So calcium nitrate should be
No, minus.
Ca.
NO3 minus 2.
Yeah, NO3.
Just like that?
No,
Minus.
but calcium.
Calcium
What?
is charged with plus 2.
No.
So, no, it's fine.
Yeah.
Ca NO3.
Take it down.
That's it.
This is it right here?
Wait.
Calcium is a charge too?
Yeah.
Yeah, that's right.
That's what it needs to be. Calcium has a charge of +2. Nitrate has a charge of -1.
Oh yeah, nitrate's way.
-1. Why did I need parentheses here?
Because it applies to nitrogen and oxygen.
Yeah. All right, so let's go take moles on the bottom. Molecules. Yep. Right here instead of atoms, that should say molecules. Okay. Molecules on top. What does moles always get?
One.
Is there an abbreviation for molecules?
I usually stop it after the C.
Yeah, I
Molic.
just put cules.
Joule.
Yeah, the important part is you don't want to stop it at mole
Yeah.
because that's confusing. Moles gets the 1. Then what always goes with molecules?
6.022 times 10 to the 20.
Good. And how do we abbreviate that so we don't have to write that out?
6. NA.
No.
No, not just 6.
NA.
If we were going to abbreviate it, we could just put NA,
Not
right? That
available.
means Avogadro's number.
Which is a little bit confusing and it's not AN.
Number of Avogadro.
It's just
Wow, this furnace is amazing.
All right, so are we expecting a big number here or a small number?
Big number.
Big. Do you remember how to use the E button on our calculator?
Yeah.
1.42 times 6.022, second EE23 gives me 8.55 times 10 to the 23rd molecules.
On tests and stuff, would you accept it if we just put
small.
Yeah, pretty small, right? Or a manageable number at least. 5.12 times 10 to the 23rd
Stop making me laugh.
molecules. Avogadro's number goes on the bottom, and 1 mole goes on the top. Do I care what substance this is? Do I need to find the molar mass? Do I even really need to find out what acetic acid is?
Volleyball players, you may now.
Okay, so here, if I take, what do we get for our final answer here?
Oh, I just deleted it.
0.885 what?
Moles.
Moles. Does that answer make sense? Is it reasonable? Did we start with more than or less than 1 mole?
That's
Less
reasonable.
than.
I started with less than a mole, right? This number is less than Avogadro's number. So that means our answer does make sense that it's less than
Wait, I
1
did
mole.
get something very different.
Oh, we got something different than that?
Well, kind of. I got 8.5. I get 8.50, not 8.
Yeah, same.
8.50?
No, 0.8. 0.850.
Got it.
Yeah.
0.850. Okay,
Yeah.
there we go. Okay.
Yeah, not 8.
How many molecules are in 633.21 grams of barium permanganate?
That's just fun to say.
633.21 grams barium permanganate.
Pomegranate.
Where is that?
Permanganate is a polyatomic ion because it ends with 8. Barium has a +2 charge. Permanganate is what? MnO4 or MnO? MnO4 what? -1 or -2? Okay, so that means my compound should be BaMNO4 2, right?
Yep.
All right.
We darn.
Alright, where is barium?
All right, so now let's start thinking. If I'm measured in grams to begin with, I need to get rid of grams and go to what? Can I go directly to molecules? No, I go to moles. Moles gets the 1, and then what goes with grams here? Molar mass. So this is BaMNO4 2. It is going to be important here that we keep the labels in because when we start doing stoichiometry, we'll have multiple compounds in those T-charts, so we want to be careful with that. Barium 137.3 plus... what did we get for our molar mass?
369.328.
I had 375.18.
Let's see, what,
We had 375.
Okay, good. All right, so from there I'm going to get rid of moles and go to molecules. Moles gets the 1 and Avogadro's number always goes with molecules. So should we be expecting big number here or small number?
big.
Big, because when I'm asking for the number of molecules, I should be expecting something times 10 to the 20 something. And I started with more than 1 mole or less than 1 mole.
More than one.
Look at the molar mass of barium permanganate. I started with more than 1 mole, so my final answer has got to be greater than Avogadro's number.
Whoa. Oh, never mind.
Did we store Avogadro's number in your calculator too?
How do you do that?
Okay, we'll do that in just a second. So let's finish this problem and then I'll show you how to do that.
Cool.
Okay, 1.01 times 10, 1.02 times 10 to the 24th
Yep.
molecules. All right, very good.